Hi guys, Audrey here. So today we're going to determine if the following series converges or diverges. The first thing we want to do is figure out which test to use. Probably the integral test, since it says integral test really big up top. That said, we always want to start with the test for divergence. So let's apply the test for divergence, or the nth term test, whatever you want to call it. So we'll do the limit as n approaches infinity of 1 over n ln n, the square root of ln n squared minus 1. And this is 1 over infinity times the square root of infinity squared minus 1, which is just infinity. So this is like 1 over a really big infinity, which is going to 0, which tells me that the test for divergence fails and we have to do something else. So our next thought should be, does a comparison test or a ratio test or a root test work? We're not going to immediately think about the integral test. Or is it geometric, or is it a p-series? Well, it's clearly not a geometric series. It's not some number to the power of n. It's also not a p-series because it's not just n to the power of a number. So we've eliminated those. There are no factorials or exponential type things, which means that the ratio test and the root test are probably out as well. However, it does have a ln n. That ln n is often a clue that points us to the integral test. More than that, though, this doesn't look really anything like a geometric series or a p-series. So finding a series to compare to might be somewhat challenging. And a lot of times, even if you do find a series that's good to compare to, the limit comparison test and the comparison test will both fail when the ln n is involved. Not always, but a lot of the time. So that ln n is really our clue that we're going to do the integral test here. So the first thing that needs to be true for the integral test is that the thing must be continuous. So is it continuous? And the answer here is yes, because, well, there are no negative n values, so I'm not going to be plugging a negative n value into ln n, so we can eliminate that possibility. The denominator equals 0 when n equals to 0, which is not on the integral. It equals to 0 when ln n is equal to 0. And this happens when n equals to 1, which is also not on the integral. And it equals to 0 when ln n squared minus 1 is equal to 0. So this is when ln n is equal to 1, and that happens when n is equal to e. Well, e is like 2 point blah, blah, blah. So here we're saying we start at n equals 3. So this is also not on the interval. Which means that as long as we're starting at 3 like we are, we're good. So yes, this is continuous. Now the second thing that has to be true is that it needs to be positive. Oops. So, and the answer to is it positive is also yes, because all of those things in the denominator are positive. N is positive. Ln n is positive. And a square root is positive. So is positive for the interval that we care about. So we're only looking at n greater than 3. Ln n is positive on that interval. Ln n is positive on that interval. Square roots are always positive. N is positive on that interval. So yes, this is positive. Now the last thing that we need to look at here is whether or not this thing is decreasing. And this one's actually pretty easy to think about. Even though the derivative might not be the easiest thing, we know that n is increasing. Ln n is increasing. And the square root of ln n squared minus 1 is increasing. So these are all increasing. So if the denominator is increasing, as the denominator gets bigger, that means the thing's getting smaller. So that means this whole thing must be decreasing. So yes, we can apply the integral test. Let's do it. So we can apply the integral test. Yay. Okay, so the integral test says to look at the improper integral. So we're going to be looking then at the integral from 3 to infinity of 1 over. I'm replacing those ends with x's, so 1 over x ln x squared minus 1 dx. And what I see is I have the derivative of ln x right there. So we're going to let our u equal to ln x, du equal to 1 over x dx. And we're going to go off to the side and do this as an indefinite integral. So that we can ignore the bounds for a moment. So we'll end up with the integral of 1 over, well, that 1 over x right there became my du. And so then this is just u, the square root of u squared minus 1 du. But hey, we know that. That's a known form. That's arcsecant. So this is just arcsecant of u, which is arcsecant of ln x. Okay, all right. Now that we've actually evaluated the integral, let's go back and think about how to deal with it being improper. So the first thing we always do is to rewrite it as a limit. Limit as t approaches infinity, 3 to t, 1 over x ln x, the square root of ln x squared minus 1 dx, which we just evaluated. So t goes to infinity of arcsecant of ln x that we're evaluating between 3 and t. So this gives me the limit as t approaches infinity of arcsecant of ln t minus arcsecant of ln 3. But this minus arcsecant of ln 3 that we have right there is just a number. It's not going to be affecting my limit. So I'm going to bring it to the outside to get negative arcsecant of ln 3 plus the limit as t approaches infinity of arcsecant of ln t. Okay, so now we need to evaluate this limit. So we're kind of looking at, and this is really bad, we really shouldn't write this, but I'm going to just so that we can think about it. What's happening at arcsecant of ln of infinity? Well, we know that ln of infinity is going to infinity. So arcsecant, and we're going to just say ln approaching infinity. So this is like arcsecant. What's happening is that goes to infinity. Okay, well, we're basically saying when is secant going to infinity? And another better way to ask this question would be like saying, when is cosine x approaching 0? Because secant x is equal to 1 over cosine x. So we're going to look at our little graph here of cosine. And we know that for the inverse trig functions, cosine is only defined between 0 and pi. So when is that cosine going to 0? At pi over 2. So it turns out that this is equal to negative arcsecant of ln 3 plus pi over 2. Which means that the integral from 3 to infinity of all of this stuff, x ln x, the square root of ln x squared minus 1 dx, converges. It doesn't matter what it converges to. It converges to pi over 2 minus arcsecant of ln 3. I forgot my, no, I did forget my c up there. Converges to that, but it doesn't matter because we only need to use this for the comparison to the series. Therefore, the series also converges. I do not know what it converges to. It does not necessarily converge to that number right there. I don't know what it converges to. I just know that because the integral converges, therefore the series also converges. And that is my final answer. That this converges by the integral test. And that is the answer. We're done. Bye, guys.